Okay, grade 11 chemistry. This is the start of our last unit. It's only 3 lessons long. So today we're going to just kind of do the knowledge and a little bit of application. Tomorrow we're doing some of the math. We're going to learn some of the pressure laws and temperature laws and stuff like that for gases. And then on Thursday we're going to be doing stoichiometry in solutions, so actually solving for a number of moles or a pressure or a volume of a gas if we're making a gas in a reaction. Here's what we're covering today. We're going to start with just layers and composition of the atmosphere, some knowledge stuff, then air pressure, what it is and how we measure air pressure, and we're going to finish with the law of partial pressures on air pressure. Then we'll talk about applications. So first, applications of partial pressures, of air pressures, and then we'll talk about air pollution and greenhouse gases because that's part of the curriculum. So we'll take that away. And we'll just get right into it. This is the atmosphere. The atmosphere has layers. There are names to these layers. And the names are given here. So the lowest layer from 0 to 10 kilometers, 0 to 10 kilometers high, is the troposphere. The troposphere is the lowest layer. Above the troposphere is the stratosphere. A lot of people have heard of the stratosphere. That's the one that people remember the most. Then there's the mesosphere. Meso literally means middle, so mesosphere. Then there's quite a big one, which is called the thermosphere. And then above the thermosphere, above 500 kilometers, is the exosphere. And the air pressure drops steadily throughout these layers of the atmosphere. Now, the official definition of space is about 100 kilometers. So I'm going to bring my stuff over to the right here. The official definition of space is about 100 kilometers high. Ooh, take that back. And you can see that here at 100 kilometers, the temperature just starts swinging like crazy, and that's where we've officially placed space. So the thermosphere actually is most of the thermosphere is actually where we'd say space is. And in fact, the space station orbits at about 400 kilometers, and this goes from about 60, 80, about 85 up to 500 kilometers. So the space station actually orbits technically within the thermosphere, within the atmosphere. It's very, 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 very thin up there. So thin that the thing can keep going without running into too much air. But it does have to boost itself up every so often because it's running into air molecules and has to give itself little boosts to stay in orbit. So troposphere is 0 to 10 kilometers. It's where all the weather happens. Tropo means to mix, so that's where the air is mixing, and there's all this weather. It's about the cruising height of a jet, the high end of the troposphere. That's where the jet planes will fly. Like the passenger jets. Then the stratosphere is from 10 to about 50. Not a lot happens there. Weather balloons go there. That Red Bull space jump guy jumped out of there, Felix Baumgartner. Like military jets can get up to that level. Then the mesosphere from 50 to 85, 86 kilometers is the middle layer. You see the temperature drop. This is the temperature in the different layers. Drop. And then in the thermosphere, the temperature ramps up like crazy. That's because there's not a lot of particles. There's not a lot of stuff for them to hit, so they can gain a lot of speed from like the sunshine and stuff. So it's you would die up here. You would actually die in any of these layers aside from the troposphere because it's so thin you wouldn't be able to breathe. But they still count as layers of the atmosphere. And because they're different temperatures, air will refract through them differently. And you get this really cool stuff. This is a picture from the space station of the space shuttle. And you can see the different layers of the atmosphere by how different wavelengths of light refract through them, through the Earth's atmosphere. It's very, very cool. The atmosphere is very, very thin as well. Even the 500 kilometer layer. Like the 100 kilometers up into space is about as thick as the skin of a basketball on the basketball. If the Earth was a basketball, the skin of the basketball would be the atmosphere, which you can imagine is quite thin. Okay, now in terms of composition, We've talked about percent composition before. It's what elements make up something by mass. Well, here it is for the atmosphere, but I believe this is by element, not by mass. Doesn't really matter. It's pretty close anyway. Nitrogen is our biggest component. 78% of the atmosphere is nitrogen, and oxygen is 21%. Now 78 plus 21 is 99. So 99% of the atmosphere is just oxygen and nitrogen. And the nitrogen is the biggest part, it's the 78%. So nitrogen, 78%, oxygen, 21%. Then the third one actually surprises lots of people. It's argon. Argon, a noble gas, argon. It's about 1%, very close to 1% of the atmosphere. So that's number 3 is argon, and number 4 is CO2. CO2. The CO2 right now is at 0.0417%, and it's growing day by day. This is an older chart because it has the CO2 at 0.038%, which would have been several years ago, certainly. Well, we can actually figure that one out. I have a graph of CO2 levels at the end of this lesson. Maybe we can go back and figure that out. And then we've got some trace gases, neon, krypton, helium, methane, and various other things. But I want you guys to know the top four. Top four: nitrogen, then oxygen, then argon, and then carbon dioxide is the vast majority of the trace gases, as you can see, and getting bigger every day. So yeah, top four. The other component that kind of changes in the atmosphere quite a lot is water vapor. You guys know this. Sometimes it's very humid out, sometimes it's very dry out. It depends on the weather, depends on where the air mass that's currently over the city came from, and stuff like that. If it came up from the south, from the States, it's sometimes very humid. Came down from the north, it's sometimes very dry. Things like that. Air can hold water vapor. Now, I don't mean steam. Steam is actually condensed water particles because you can see them. Remember, in a solution, it's homogeneous. There's water vapor, invisible water vapor in the air right now, and so it's kind of humid. And the air can have more of that water vapor in it the hotter it gets. It's kind of like a solubility law. It's actually an equilibrium thing. You can look at the grade 12 content for that if you want. There's some equilibrium stuff in there. And that's where we get the percent humidity. The percent humidity is what percent of the absolute maximum, the saturation point of the air, what percent of the maximum water the air is currently holding. That's relative to humidity. So like in cold weather, the air can hold less air, so you need less. The air can hold less water, so you need less water in the air to get a particular percent humidity. And hot temperatures, you need more water in the air to get a high percent humidity. On the absolute hottest, most humid day, water vapor can be up to 5%, up to 5% in the atmosphere. So anywhere between 0 and 5%. Typically, you're looking at 1 or 2%, which actually puts it into third place in terms of components of the atmosphere. So typically, it's actually water vapor. It's like nitrogen, then oxygen, then water vapor, then argon, and then it kind of flips like back and forth. In the winter, it can be very dry because it's so cold. In the summer, it's usually in third place, kind of stuff. So it's water vapor. Here's a graph of that saturation point. You see just how quickly the amount of water fraction increases with temperature. So like if it's 15 degrees outside, the water can easily hold 1% of the air. You can look up your current relative humidity if you want, and then figure out how much water the air is holding. You know what? Let me do that. I'm going to pause and look that up. Okay, so I looked it up, and according to Environment Canada, currently the humidity is 37%. The dew point is 6 degrees, and it is 17 degrees outside. So if it's 37% humidity, and it's 17 degrees outside, the maximum the air can hold is something like, 1.5%, something like that. And we're at 37% of that. And that's where we get the dew point. The dew point says it was 6 degrees. So if it goes below 6 degrees outside, the air can't hold as much water as it currently has right now. That's what the dew point is. And so if I suddenly make it colder than 6 degrees, we will see the water actually come out of the air. The water vapor will turn into a liquid. And that's like if you take a cold drink out of the fridge and you see the water start forming on it. That's actually coming straight out of the air because of that dew point. You're below that dew point. This is also what creates clouds. Right? Air gets colder with altitude. We see that in the atmospheric layers. See how in the troposphere it gets colder with altitude. I'm going to bring my thing over. Troposphere, it gets colder with altitude. It's about 10 degrees. It loses about 10 degrees per kilometer. And so as that humid air rises, because it's warm and humid, it gets colder. And when it gets past the dew point, that's right now it's 6 degrees because of how humid the air is, it condenses out into droplets, and that's what we see as a cloud. A cloud is liquid water droplets that happen above the dew point. And this is why clouds form at a consistent height. If you've ever looked at clouds and you see them form at a very specific height, that's why it's happening. So yeah, that's the composition of the atmosphere, the layers, and a bit about water vapor and how it forms. Our next piece is air pressure and measurements of air pressure. So right now, my app tells me that the air pressure is 102.9 kPa, and it's dropping, whatever kPa is. We're going to talk about that, how to measure air pressure and what a kPa is. I'm going to pause and I'll get there. So air pressure, measuring air pressure. First off, where does the air pressure come from? Well, it comes from the fact that gas has mass, right? It's made out of molecules. They're all over the place. They're floating in the air, but they do have mass. It does have a certain amount of weight, and it's affected by gravity. So gravity will pull down on the air. That means that there's more air molecules near the bottom than there are further up. And that column of air above you, that 100-kilometer column of air above you, has a mass, and it's pressing down, and it's pressing in all directions. It's trying to press in on me. That's what air pressure is. It's the strength of the collisions of those air particles as they hit me. There's lots of them, and they're hitting me all the time. In a typical room about this size, there's about 50 pounds of air, and it's all flying around like crazy and hitting me all over the place. And that's the pressure that's pushing in. If I suddenly disappeared, there would be a void here, and the air would rush in to fill it. And that's what it's trying to do by hitting me with air pressure. And this is why air pressure decreases with altitude. As you go up, there's air underneath you, and so as you go up, you get lower air pressure. Barometric altimeters are actually very, very useful. So for example, my smartwatch actually has a barometer in it, something that measures air pressure, and it tells me how far up and down I've gone. I think it uses it to count how many steps I do every day, like how many stairs I do every day. So that's why air pressure will decrease with altitude. So like Mount Everest, the air pressure is about a third the air pressure in at sea level. There's these numbers. 101.3 is the average sea level air pressure, and on top of Mount Everest it's about 33 kPa. Right now here it was 102.9, so we're actually at a higher air pressure than the average. We just have a high pressure system in here. I can tell because there's no clouds. Now measuring air pressure is interesting. One of the earliest ways to measure it was the mercury barometer. Basically, remember the air is constantly colliding with surfaces, and so what they worked out is they could take a tube, fill it with mercury, and invert it into a pool of mercury, and the pressure of the air pushing down would push the tube of mercury up to a certain level, which was the air pressure. Right? The air pressure was pushing it down. If the air pressure was higher, like it is today, that you saw is 102.9, that mercury column would be higher up because there's more air pressure around the little thing, so it would be higher up, so you'd get a higher level. And then if the air pressure was lower, then this could drop a little bit more because there wasn't as much force pushing it up into the tube. That's the mercury barometer. They found that on average at sea level, the air pressure could push up a 760 millimeter column of mercury. So the column of mercury could go up 760 millimeters. They used mercury because it's so dense and still a liquid. If you tried it with water, you would need a 10-meter high column, for water. So that's like 5 floors or something, 4 or 5 stories. Certainly, you need a whole like building to make the column. But with mercury, 760 millimeters, so less than less than a meter. Think about a meter stick. That's about how big you'd have to be. The thing would have to be. This is an old measurement, millimeters of mercury, but it's still used for blood pressure. The numbers you get on a blood pressure machine, on like 116/68 here, that is in millimeters of mercury. So your blood is actually at a lower pressure than sea level. Your blood is at a lower extra pressure than sea level, I should say. It's already at sea level pressure when it's equal with the air pushing down, but then your heart can add in an extra push of pressure to make it push through the veins. So that's how that works. That's air pressure, and that's what the numbers, the millimeter of mercury, mmHg, means. So some units. You saw kilopascals earlier. Here they are, kPa. That's from the SI unit, the Système International unit of pressure, and that's named after Pascal, Blaise Pascal, who did a lot of measurements of air pressure. Famously, he would take one of these barometers, these heavy mercury barometers, and he made his assistant go up to the top of a mountain and then back down and measure the pressure difference on different days and stuff. He took the credit. Of course, you do. But the SI unit was named after it. It's 1 Newton per square meter. If you've taken physics, you know that Newton is a unit of force. Square meter is area. So if you push on a square meter with a certain amount of force, that's 1 Newton. It's a very small unit of measure. A Newton is about the weight of this cup. This cup has a weight of about 1 Newton as it's pushing down. And a square meter is quite big. It's about this, like a table. Like a table. So imagine like you're holding up a table and there's a certain amount of pressure, and then you put a cup on the table. There's a little bit more pressure. That increase in pressure of that 1 cup on top of that table, that increase in that pressure, that's 1 Newton. 1 Pascal. It's very small. So usually a kilopascal is used, which is 1,000 pascals, just like a kilometer is 1,000 meters. So yeah, that's 1,000 newtons per square meter. It's 200 pounds on a square meter. It's like a person standing on a table, and that's how much pressure the table would push into the ground with, the whole surface of the table together. Now the imperial measure of this is the PSI, the pound per square inch. This is the one that more people are familiar with. It's also much more evocative. A pound on a square inch. Your thumb is about a square inch, so 1 pound of pressure with your thumb, being able to hold up a pound with your thumb, that's 1 psi. It's bigger than a pascal or a kilopascal, 1 pound per square inch, because it's a small area, so it's a stronger pressure. The equivalence in atmospheric pressure, I'll bring this over here. 1 atmosphere, so the average atmospheric pressure at sea level is 760 millimeters of mercury. We saw that earlier. It's 101.3 kilopascals. Right, kilopascals. So 1 kilopascal is like a person standing on a table. Put 101 people on a table. That's air pressure. That's the air pressure. That's how much the table would push into the ground. Or 14.7 psi. 14.7 psi. So about 15 pounds per square inch. So imagine trying to hold up a 15-pound weight with just the pad of your thumb. That's how much pressure the air is currently pushing on your thumb with. It's actually pushing right on your thumb with that. So your thumb is pushing back with that much pressure as well. That's because we have an internal pressure that's equalized to the external pressure. Now we're getting to the law of partial pressures. So I'm going to pause again, and then we'll get into that. This is Dalton. Okay, so partial pressures. This comes from Dalton. Dalton was a meteorologist. He was also did the particle model. Right, Dalton's particle model, the first kind of atomic thing, where it's like there's a particle of hydrogen and a particle of oxygen and stuff. He said that each individual gas in a mixture has its own pressure. So basically the idea is there's a bunch of these little gases whizzing around, and there's some nitrogen here, some oxygen here, some argon and stuff. And the argon collides with you, and the nitrogen collides with you, and the oxygen collides with you, but each one is doing its own collision, so each one is exerting its own pressure. And as Dalton figured out, it's straight up the number of molecules. It is not the molar mass, it's not based on weight, none of that. It's the number of molecules that defines how much pressure each one makes. So this is not based on molecular weight. Nitrogen is slightly lighter than oxygen. Nitrogen is slightly lighter than oxygen, but it doesn't mean that each individual molecule of nitrogen has less of a collision, less of a pressure than each individual molecule of oxygen. It's just based on their partial pressures. So that's that, right? The total pressure is the sum of all partial pressures, and each gas has its own partial pressure. And that's what's going to be important in like reactions of gases and stuff. It's on partial pressure, not total pressure. It's the pressure of that specific gas that matters. So yeah, we'll have some examples of that in a second. So basically the total pressure is pressure 1 plus pressure 2 plus pressure 3, and you can see that here in this chart. Nitrogen is 78% of the air. It's also about 78% of the pressure. Right? The pressure in pascals is 101,000, so it's a little bit more than the 78. So it's 78% of the pressure, or 0.78 of an atmosphere. Oxygen is 21% of the air, and it's 21% of the pressure. Argon is about, 1% of the pressure, because it's about 1% of the air. And carbon dioxide is, again, this is an old chart. This is 0.039. Now it's 0.042. We've gained almost a percent on that, almost 10% on that since this chart was made. Yeah, that's partial pressures. I believe we're next up into applications. So let's talk about applications of partial pressures. Okay, so partial pressure applications. The first one is something in space, and one thing to keep in mind, humans only need about 2 psi partial pressure oxygen to live. Where that comes from is that air is 14.7 psi, about 15 psi, and oxygen is about 20% of the air. Right, so 20% of 15 is about 3, but we can survive higher altitudes. We can live at higher altitudes, all the way up to like 6 or 7 kilometers in some cases. So for example, when you're up in an airplane, it's only pressurized to about 70% of air pressure. So we're okay. We can get away with about 2 psi partial pressure oxygen, and we're fine. We're okay. We breathe completely normally. And so in early spaceflight, they took advantage of this by using 100% oxygen in the atmosphere, but at very low pressure, because it was simpler. You only needed one tank, just an oxygen tank. You could fill up the capsule with a lower pressure, so there was less chance of like leaks and stuff like that. And it was actually a decent decision. The problem was oxygen makes things very flammable. This is why the low pressure was important. If you kept it at a low pressure, the reactions would go the same rate, and the humans would still be able to breathe at the same rate and everything. So Apollo, the one that actually landed on the moon, used 100% oxygen, but it was only 5 psi. The pressure in that cabin was a third of normal air pressure, but it was pure oxygen, so the partial pressure of psi was actually higher than typical partial pressure of oxygen. So they were able to breathe. They actually were getting more oxygen, much more oxygen, twice the oxygen that they needed. But there was a problem there because of pressure differences. Up in space, no problem. You pressurize the capsule to whatever pressure you want, because outside there's zero pressure basically, so you can pressurize whatever you want. But on liftoff, you've got the outside air pressure that's trying to push in on your capsule, and they didn't want to have a pressure difference between the outside and the inside. So what they did was on liftoff, in this specific case, in Apollo 1, they pressurized the inside with their pure oxygen tanks until it was equal to the outside pressure, actually greater than the outside pressure. They pressurized to 16 or 17 psi, so greater than the outside pressure. And that led to a 100% high pressure oxygen environment. And there was a spark and a fire, and the 3 astronauts actually died in the high oxygen fire that followed. There was all kinds of bad design decisions there with the hatch and stuff like that. They had to redesign the hatch later. But they still flew the oxygen atmosphere because it saved them so much weight. So, Neil Armstrong and Buzz Aldrin, when they landed on the moon, and all the other people that landed on the moon, they actually were breathing pure oxygen the whole time, and nothing bad happened. And it was low pressure, pure oxygen. That's kind of neat. And the other thing is the bends. Humans are pretty resilient to pressure. If the pressure is all around us, our inside will actually equalize the outside. And you've felt this probably if you ever had your ears pop when you're going, down or up a hill in a car, like a big steep hill, or taking off or landing in an airplane. The air pressure is equalizing and your ears pop and stuff as your body equalizes to the outside air pressure. But once it's equalized, you're fine. And we're very, very resilient to this. As long as the pressure inside us is equal to the pressure outside. So, for example, the scuba world record, 332 meters, is over 30 atmospheres of pressure. 30 times more pressure than we feel in a normal day. And even that, remember the normal atmosphere pressure is 15 psi. It's 500 psi. Take your thumb and 500 pounds of pressure on it. 500 pounds of pressure on your thumb. And people did that, no problem. With a scuba suit. But it's not like the scuba suit helped against the pressure. It's just scuba. And of course, whales and submarines are even better at this. So like there's the sperm whale 3 kilometers down, so like 5,000 psi, 5,000 pounds on each square inch, and the deepest, the Challenger depth, is about 11 kilometers down. So that sub had to handle, tons and tons of pressure on each square inch of the sub. They're basically made as a giant sphere because that's the strongest they can be. Now there's a problem there, is that as the pressure increases on you, air becomes more soluble in your blood. We talked about that in pressure trends. The pressure on the outside makes air more soluble in your blood, and nitrogen in particular will get more soluble in your blood. And if you spend long enough down in the depths, that nitrogen will slowly dissolve into your blood. And slowly is the key there. So the longer you spend, the worse this is going to be. And then on decompression, when you come back up, now the pressure is coming off of your blood, it's coming off of your body, and the nitrogen suddenly bubbles out. And it can be very, very painful. If it happens, if there's enough air bubbles, it'll lead to like cardiac arrests and stuff. But mostly, and the reason that it's called the bends, is that it comes out in your joints. Your joints have fluid in it, and the fluid has air dissolved in it, has gases dissolved in it. And this is actually how cracking your knuckles works. You reduce the pressure as you crack it, and you get that pop. The pop is the air coming out. But this is like all your knuckles getting cracked at the same time and like over pressured. And so that's why it's called the bends, because it gets painful to bend your fingers and your joints and stuff like that. So that's nitrogen gas bubbles in the blood and the joints and stuff like that. That's the bends. They try to avoid it by breathing different gases if they're going down further. They take stops on the way up and have a certain amount of time that you just have to sit there and decompress, stuff like that. The really deep sea, like welders on oil rigs and stuff, they actually have a special cabin that they go to avoid all this decompression stuff. They have a special cabin they go to, and they actually live on the seafloor for a while as they do their work, and then they come back up, because going up so slowly would take too long and be too expensive and stuff like that. So they actually live on the seafloor for a while. All right, last piece is air pollution and greenhouse gases. We're going to pause that and get there. Okay, the last piece is greenhouse gas emissions. I'm sure you've heard a lot about CO2 and environmental stewardship and stuff like that in your high school career so far, and I'm going to say my piece about it too. This is part of our curriculum, so it's right in there. We want to talk about sources of greenhouse gases and things like that. This is specifically greenhouse gases. This is from 2017. And you can see the different sources of greenhouse gases. Our total kilotons of CO2 emitted, 760,000 kilotons. So that's a lot of CO2. We're one of the highest per capita, mostly because of heating in the winter. We have a lot of greenhouse gas emissions from heating and stuff. And this is tracking the percentages of the total. So if I move my stuff over, we have the biggest piece of the pie is mining, quarrying, and oil and gas extraction at 24%. 24%. Utilities and manufacturing together come together for about 30%. So more than half of our greenhouse gas emissions as a country is kind of heavy industry, right? Utilities, construction, manufacturing, mining, oil and gas extraction. And the next biggest piece of the pie is households. So households, this thing behind my head here, households, is almost 20% of our greenhouse gas emissions, but it is 20%. So just heating up your house and that kind of thing. So that's households, and then forestry, fishing, hunting, agriculture, about 10%. And then behind that is transportation. So this is something I really want to talk about. I like talking about this in the case of, say, electric cars, right? People get electric cars and they're saying that they're doing their part for the environment, which, fair point, yes, electric cars do help the environment. I'm not saying don't get an electric car, but it's not as effective as people seem to think it is, because only 8-9% of greenhouse gas emissions are transportation and warehousing. Plus there's some from the oil and gas extraction to put it into your car in the first place. So we might call it maybe, I don't know, 15-20%. But out of that, this is just transportation. This is the transportation section in total. Passenger cars and passenger trucks take up about half of the transportation section. And so electric cars are great. Electric cars are great, but you're talking about half of 15 or 20%. You're talking about maximum about 10% impact in switching to an electric car versus driving a gas car. So yes, it's a good thing. It's 10%, but it's only 10% of a change. We gotta think about that. And various other things, right? It's more effective. It might be more effective to just reduce our consumption of stuff. Utilities and manufacturing and stuff like that. That's a bigger chunk of the pie. Agriculture, forestry, fishing, and hunting. Most of this agriculture is beef and chicken and stuff like that. So a lot of people say that cutting out some meat is a good way to reduce your greenhouse gas emissions. There's a lot of things besides just cars and transportation is what I'm getting at. Cars and transportation, maybe 10%. Maybe 10% of a typical person's greenhouse gas emissions. But hey, electric cars are cool. I like them. Just, it's not as powerful as people think. All right, greenhouse gas effect. So you guys know about the greenhouse effect, probably. We've all learned about it. Basically, sunlight comes and hits the earth gets warm, and you've probably felt like if you're in a concrete city and you feel how hot the concrete gets, it's giving off heat. It gives off heat in the form of infrared radiation, and that's the stuff that the CO2 will catch, and the methane and stuff like that. It's the radiation given off by the hot earth. Not the incoming sun, it's the outgoing sun that it catches, the infrared. And so it takes that, it catches it, and then heats up the atmosphere because it's catching it instead of just letting it go off into space. And then the atmosphere heats up, and the atmosphere heats the earth up. Then the earth heats up the atmosphere, and the atmosphere heats up the earth, and the earth heats up, and things just get hotter and hotter and hotter. And more CO2, more greenhouse gases, means that it gets hotter faster. We actually need the greenhouse effect. We need a certain amount of greenhouse effect, or else the earth would be too cold to sustain life. But the theory goes that because we're releasing so much CO2, we have outstripped the natural greenhouse effect, and we're not sure what the effects are going to be. Changing the energy balance of the troposphere changes the weather patterns. It changes all kinds of stuff. It changes how animals are going to move and live and stuff like that. Making a warmer ocean means that less oxygen can dissolve into it, and the animals might have to move. It's not good. Here's greenhouse gas emissions by sector. These are the greenhouse gases themselves. So this is something else I want to talk about. There are different greenhouse gases. Carbon dioxide is most of it. Notice, more than 3/4 of it is carbon dioxide, but a hefty chunk of it is methane. Methane is a greenhouse gas. This is stuff that comes out of burps and farts and stuff like that, mostly bacteria that produce methane. And nitrous oxide is also a greenhouse gas that's used in the fertilizers and things like that. So methane produced by burping and farting animals, and nitrous oxide produced by agricultural stuff and plants and stuff. You might imagine that's going to make up a lot of our agricultural greenhouse gas emissions, and it does. Right? So down here, carbon dioxide is pretty evenly split between things. Right? Except look at the agricultural. Almost no carbon dioxide from agricultural. That's because there's so many plants and stuff. They'll absorb CO2. But look at the methane. 40% of the methane comes from agriculture, and 62% of the nitrous oxide comes from agriculture. So yeah, agriculture is very bad. Also a lot of methane from the fossil fuel retrieval. And methane's about 300 times worse as a greenhouse gas than carbon dioxide. So it's quite a strong gas as well. You'll actually see the methane in oil refineries. They will burn the methane to turn it into CO2 because the CO2 is a less powerful greenhouse gas than the methane would be. So burning it is actually helping the environment because they have to release the methane. I don't know why. I guess they could capture it and sell it to people, but it's better for them to burn the methane because the methane is worse as a greenhouse gas than the CO2 that would come off of burning the methane. Yeah, and that's the same thing, greenhouse gas emissions by sector. Okay, now the last thing I was talking about, carbon dioxide. We see the carbon dioxide going up year over year. This is, you can see the years down here, year over year over year over year. And you see this cool seasonal variation. It goes up and down and up and down and up and down in a very, very specific pattern, season by season. And what that is the carbon dioxide level on Earth is actually lower in the fall and higher in just before spring. And that's because the plants, as they grow in spring and summer, will absorb CO2 to build more plants. And then as they die, over the winter, they won't release the CO2. Or they'll release that CO2 and they won't absorb new CO2. So we see this seasonal variation in CO2 levels. So they peak sometime in May every year, and they drop to their lowest sometime in, I think, October, something like that. And the reason that it follows spring and summer and fall and winter in the northern hemisphere is because most of the land mass and most of the plant mass is in the northern hemisphere. And so that's what the CO2 levels follow. So remember I said we could check when that thing was made? Well, 380 ppm was about 2005. So we can tell way back here, all the way back at the start. Here, 0.038, this would have been probably from about 2005, maybe 2008. Over 10 years old for sure. Because these days, the CO2 level is about 417 ppm, which isn't even on this chart. It's up here. 417, maybe? 390, 400, maybe 410. Yeah, somewhere about there. So you see the trend has been going on. And here's a look further back. 1750, 1800, we have this very flat CO2. This is from like sea ice measurements, like ice core measurements. And very suddenly it started going up, and it's just keeping on going up. Remember, it's 417 now, so 35, 36, 37, 38, 39, 400. Yeah, this would be off the chart by now. And somewhere about here. So we've followed the trend. We've kind of flattened it a little bit, but yeah, it's not great. So with that, on that depressing note, that's the end of the lesson. We have covered layers and composition of the atmosphere, air pressure and pressure measurements, the law of partial pressures, some applications of partial pressures, the Apollo 1 fire, and the bends. We talked about why your knuckles crack. This is fun. And then air pollution and greenhouse gases. We ended on a bummer. That's it for today's lesson. Sorry for the weird tangent about electric cars. It's just a personal thing of mine where people act so high and mighty with their electric cars. I still want one, but I just think they're not as powerful of an environmental tool as people seem to think they are. Yeah, that's it. Thanks for paying attention, and I'll see you guys in class.